So there are two things I want to look at really today. Aims is, first one is to look at formulae. The most important thing that we need to do is to be able to rearrange formulae. The one that we've looked at already, Ohm's law, V equals IR. V is the subject of that formula, but sometimes we want to find I or R, so we need to rearrange it to make I or R the subject. And that's quite a skill to rearrange formulae, particularly when the formulae get a bit more complicated. But initially, I want to just look at using formulae. So putting in large numbers, putting in small numbers, what do you do about the accuracy, stuff like that. And units, which is always a big issue. So that sort of thing to do with using formulae. Coping with large and small numbers. What accuracy do you give your answer to, and what do we do about the units and these things? And then we'll make a start on that. We'll have a look at an example, and then we'll have a break, and then maybe do a few questions around that. And then the other thing I want to have a look at today is just to introduce this third assignment, so which is to do with statistics. So just look at that, and we'll look at presenting data, and I'll set you off on where to look for this sort of thing. So a lot of this is going to be self-study, and then you can have maybe make a start and looking at the questions for this particular assignment between now and next week, because you'll have access to the chapter because I'm putting it on the website, and you can try the questions. Okay, so I'll show you about all that, and then we'll start. So that's the plan. So formulae, I've just jotted a few down on the board that I thought you may be, or some of you may be familiar with. Anybody recognise any of those formulae? Velocity equals, well, velocity and speed are the same thing, yeah. So velocity, distance divided by time. So why do you think this is the letter S? D is for distance. This isn't distance. No, not speed. Yeah. Displacement, yeah. And distance and displacement aren't quite the same thing, are they?
No, displacement has direction.
Yeah, which makes it a vector. Yeah, that's right. So displacement is a vector quantity, and distance is a scalar quantity. Go 3 kilometers, distance of 3 kilometers. Go 3 kilometers north, that's a displacement. Okay, because it's got a direction associated with it. So we tend to use, in this formula here, velocity. Again, velocity is the vector equivalent of speed, so speed and velocity are interchangeable, but velocity is the vector equivalent, is displacement over time. Good, that's one formula. So if I want to find the velocity, what do I do with the displacement and the time? What's this formula telling me to do? Divide. So S over T means S divided by T. Any other formula that anyone recognises? Well, this one. What's that again? Ohm's law. Any others? That one? Power, right. Power equals no I current. Yeah. Power, to get the power, what do I do with the voltage and current? Times them together, because no symbol means multiply. So power is volts times current. That's another familiar equation if you've done any electrical work. So these two formulae are pretty basic electrical formulae that you'll use. Any others? Yep.
Is the right resistance parallel?
Certainly is, yes. 1 over RT, so RT stands for the total resistance, So note this use of symbols. This is another very common thing. Use a capital letter to represent the resistance, say, but if I've got more than one resistor, as I have in this formula, then the subscripts are used. So T, total resistance, not surprisingly, R1 and R2, so I've got two resistors, R1 and R2, and this is a way of finding the total resistance for those in parallel. Yeah. Yeah, no, it's not, unfortunately. That 2 is parallel. This bottom left one is for finding resistance in parallel as well. The total resistance RT is R1 times R2, because they're next to each other. Yeah. Divided by R1 plus R2. And if you've done any work on electrical, people often remember it as the total resistance in parallel is product over sum. Product multiply over divide by sum, the addition. Yeah? Okay, product over sum. So they're both for resistors in parallel. So that means these are, in fact, the same. And algebraically, if you had enough confidence with the algebra, you would be able to rearrange that formula to get this. And if you want to have a go, we've talked already about what's involved here. These are fractions. And to be able to add those fractions together, what have we got to do with the denominator? Make it the same. So if you would like to puzzle over that, you might be able to arrive at that formula from this one. Okay? So that just leaves this one here. Anybody recognise that? It's for finding the pressure in a liquid or the atmosphere. And so the P stands for pressure in this formula. So that's another problem we have. P can stand for different things. P stands for power in this formula, but pressure in that formula. So, you know, we use the same symbol to represent different things. That symbol there is an interesting one. That's actually a curly symbol, not P, it's rho. So this is part of the Greek alphabet. So this symbol here, because we run out of ordinary alphabet letters, then we use pretty well all the letters in the Greek alphabet as well. So that's worth getting familiar with. That's the Greek letter rho. It looks like a P, you might say, but it's a curly sort of thing like that. Rho.
What does rho stand?
In this case, rho stands for the density of the liquid or the gas. G, the gravitational constant, and H, the height or the depth. So to find the pressure, it's the density times gravity times the depth in the liquid. So, is it Jack at the back? No, sorry. Next to you. Yeah. Cameron. If I want to find the pressure, I need to know that. What does that stand for? Do you remember? Density times gravitational constant and the depth. So if I know the density, the gravitational constant, and the depth, what do I do with those three things, Cameron, to get the pressure? Times them together, yeah. Okay? So let's have a go at one. You've got your calculators. They're allowed. Find the pressure for that problem. You're told that G is 9.81. That's the gravitational constant. And that's a constant, 9.81. The depth is 3.62 meters. And the density for this particular liquid is 13,600 kilograms per cubic meter. So calculate the pressure.
Makes no difference in which order you time.
No, it doesn't. That's a good point, Cameron.
So whichever way, if the G was in replacement for H, it wouldn't make a difference in the
No. No, in fact, I've written it differently, haven't I? H rho G, and then the previous one wrote, actually the order of symbols doesn't matter. In this case. Let's have a look at this thing together then. So, Callum, where are you, Callum? Callum, can you tell me what answer you got for the pressure? Oh, are you? Okay. Who's sitting next to you? Ricky. Point 60. Is it somebody else? There's that sort of 492,965. Anyone else? Something different? You got the second one? Yeah, that looks better because I've done this already with another group. So just check that. You're timesing them together. Ah, I can see the problem. It's a phone thing. Yeah, so yeah, you'd been far better off if you had a scientific calculator. That looks like the answer. Okay. The kilonewton meters. You can use kilo. We've not done that yet, but not newtons per meter. No, newtons per meter squared.
So what would be the one that you'd use as the unit?
Newton per meter squared.
Newton meter squared.
Yeah, Newton per meter squared. Newton per meter squared. And there's another name for that. Anybody know it? It's often called a Pascal. Yeah. Same thing. 1 Pascal, PA, is a Newton per meter squared. So if you're measuring newtons in meters squared, then you're measuring pascals. As a little aside, we were talking about units, Cameron. So the unit for pressure is the Newton per meter squared. And so that unit times that unit times that unit should give this unit. So newtons over kilograms per kilogram multiplied by meters multiplied by kilograms per cubic meter should give this. And if you look at it, look, kilograms cancel, top and bottom. One of the meters on the top cancels with one of the meters on the bottom, leaving meters squared, and you end up with newtons per meter squared. And so that's, you can, if you don't know what the unit is, you were saying, Daniel, with a bit of algebra, you can actually work out what the unit is. Which brings me to another point, which is that before you put the numbers in, you should check that the units are consistent. What do you think I mean by that? Yeah. If this was not measured in meters but in centimeters, what would I have to do? Change it into meters. Okay. If this was not measured in kilograms but grams, I'd have to change it to kilograms because that's in kilograms. The units must be consistent. So if you're using G, which is the gravitational constant, that implies kilograms and meters. So you must be in meters and kilograms. And then you can cancel out the units and end up with the right unit at the end. So I've given you one where the units were consistent, but if they're not, that's the first thing to consider. Are the units consistent? If the units are consistent, then you're quite safe to put in the values into your calculator and get this answer. So the pressure is that. And so now we can put the unit in pascals. If I'd asked you to do that at work, go on.
With the units,
Yep.
Would it be to the would that be to the minus 2?
Yeah. So this Newton per meter squared, because of something called the laws of indices, we can write divide by squared something as times to the minus 2. So that's equivalent to Newton meters to the minus 2. So they are the same. Yeah, so thanks for that. You might see that written too. So I could measure this pressure in pascals, newtons per meter squared, or Newton meters to the minus 2. They're all the same.
Will it be tested like a proper test?
No. This is all I'm doing is I'm giving you lots of stuff that you are going to come across in other units. You'll see that and you'll see that. They're the same. Don't let that confuse you. Okay. You mentioned that, oh, we're not going to test this and sort of, but actually in a way you are, because your whole engineering career is going to be testing this sort of stuff. So this is basic, okay? If you were at work and if I was your boss at work and I'd asked you to do this, we've got this instrument we're going to set up. This is actually the density of mercury. So we've got a mercury column. And at some point in this mercury column, 3.62 meters down in this mercury column, you've been asked as a technician in the company or an engineer in the company to calculate the pressure at that point. So you go away and you come back and you say to your boss, that's the pressure. He's going to say to himself, oh, that's good, he's put the pressure units in, but I'm not very happy with that as an answer. That shows a lack of experience, a lack of understanding of the problem. What's wrong with that? Yeah. Sorry. Standardize it. What do you mean by standardize it? Ah, right. Okay. You can use standard form to shift this around. So I can go 482.96592 times 10 to the 3, that sort of thing. Or kilo. Yeah, we'll come to that. But that's not what I'm after. Yeah. Yes. Good point. I'll repeat that because for this and also for everyone else, it's only accurate to 3 significant figures. What do you mean by 3 significant figures and why 3?
Well, each of the numbers, GH and density,
Yeah, are accurate to 3 significant figures. What that means is someone's measured this, and if you look up G, the gravitational constant, actually you can get it more accurate than that. Okay, but it's been quoted to 3 measured values, 9.81 newtons per kilogram. Someone's measured the height with a meter rule probably and measured it to the nearest centimetre. Look, 3 significant figures. 3 measured values. That's what we mean by significant figures. That number, and that number have been measured. How many significant figures in here? 3. This 0 and this 0 have not necessarily been measured. They're only there to make sure that these 3 numbers are in the right column. Right, Daniel? That's got to be in the 100,000 column, the 10,000 column, the 1,000 column, and the hundreds column. So I've got to have the 2 noughts. Does everybody see that? They're not necessarily significant. If they are significant, they would have to be quoted as significant. But as it is not, we'd take it as read that that's just 3 significant figures. So how can my answer possibly be more accurate than 3 significant figures? It can't. Your calculator just carries on calculating what that times that times that is until it runs out of space on the screen. If you had a bigger screen, it would go on and on and on, wouldn't it? Where'd you stop? That's where the accuracy comes in. So I want to quote this figure to 3 significant figures. So what am I going to do? Try and write down what you think that is to 3 significant figures. By that I mean 3 measured values. There's the first measured value, and so on. So I only want 3 measured values. So have you written down an answer? Not yet? Yeah, at the back. 483. I'm glad you said 1,000 because I've got to put the noughts on to keep the space, keep the place in the column. Pascals. That's right. First significant figure, second significant figure. Let me just indicate it for the video thing. First significant figure, second significant figure, third. So what I do then is look at the next one. I ignore these, the 6, the 5 and the 9 and 2 and everything else. They're totally unimportant, just the next figure. And if that's 5 or more, I round that up to 3. If it's less than 5, I leave it as a 2. So the 5, the middle one, we go up. 5 or more go up. So 483, and then the others are just to hold the place, 483,000. So now what I do is, so that the person I'm giving this calculation to knows I've rounded it to 3 significant figures, I write 3 significant figures. So if I were to give that as the answer, then the person I've given this to would know I'm talking to someone who's a confident engineer who knows about accuracy.
But surely the one which hasn't got three significant figures is more accurate.
You'd think so, wouldn't you, Daniel? But no, it's just the calculator doing that. What gives it the accuracy is not the calculator, it's... Remember, this is a real situation. You know, we're finding a real pressure. So the accuracy is to do with how accurately you've measured the height and how accurately you've measured the density of the liquid, not how good the calculator is dividing numbers. That's just the maths. Do you see the difference?
Yeah.
So the accuracy comes from the measuring, not from the calculator. And we don't bother with decimal points generally. I know some lecturers will and some people do, but always think of the significant figures, because the position of the decimal point, if we look at this particular measurement here, if I'd have measured it in centimetres, I'd have had 362 centimetres. But it's still only 3 significant accuracy. But if I'd measured it in centimetres, it would have no decimal places, whereas now it's got 2 decimal places. So we don't go by decimal places, we go by significant figures. Okay? So, and the other thing is, of course, in this particular one, I gave all of them as 3. What happens if one of them was 2 and all the others were 3? What effect does that have? Really, I should only go to 2, because that's the accuracy. If I'd only measured this as 3.6 meters, that's my least accurate measurement. So how can my answer be more accurate than the least accurate measurement I put in? The rule of thumb is your accuracy is the same as the least accurate figure you put in, or one more. You can go to one more, but no more than that. So if it had been 2 and these others had been 3, I'd have probably gone to 3 again. Okay, so accuracy. One more thing and then we're going to have a break. Cameron, you mentioned the idea of kilo and so on, or using... so instead of writing 483,000 pascals, I could write, or if it wasn't you, someone was talking about these in the middle here, I could write 483, what's 1,000 pascals? A kilopascal, to 3 significant figures. So I could write 483 kilopascals to 3 significant figures, because 1,000 pascals is 1 kilopascal. I'll summarize all this with a note. So, using formulae, not quite as straightforward. There are a few rules you need to remember, and these are them, you know. Think about the units. Are they consistent? If they are consistent, then you can plug the numbers into your calculator. Once you've done that, you need to think about the accuracy. And then you look back at the original measurements for that. Once you've got the accuracy, you might, if you've got a very big number or a very small number, decide to use some sort of prefix like a kilopascal. Okay, we'll pause there and go and have a break.